Welcome to Solar Study course. Now we go for the lecture 3. See, in lecture 2 what we have learned? We have learned about the basics of a photon and electromagnetic waves and other thing, how energy equation has been formed, how we can derive that and all we have studied. In lecture 3 we go for the properties of the sunlight and spectral irradiance and the little inside of the photon flux. Myself Karthik M. Let's start the lecture 3. The course outlines are: what is the photon flux? How photon density, it is nothing but power density of the photon, and we will cover the spectral irradiance. So first of all we learn the photon. Then I have told that if more number of photon is incident on the area, then it will become the photon flux. So number of photon is the incident on particular area. This is called photon flux. So let's consider if area or anything, it is maybe in a circular or in a square shape, if more number of flux is incident on the particular area, let's consider in 1 second, that we will denote it as a phi. So phi is denoted by number of photons incident per area. What is the area of any square or any is meter square? In time we can call it as a second. So photon flux formula is denoted as number of photons incident per unit area at 1 second. This photon flux is very important to know about the how much electrons are present in solar cell. As we know, high frequency photon, it is indicated like this, which has a lower wavelength, and low frequency photons, it is denoted like this. Here frequency will be low, here frequency will be high. So in this image you can clearly see this is the high frequency photon, this is the low frequency photon, this is particular area. So we will get the photon flux. Next, for any given wavelength, the combination of photon wavelength or energy of a photon at a particular wavelength can be determined. So by using this one, we will get the power density of photon for a particular wavelength. So we will derive some equation for the power density. How? See, in this one, let's consider SI unit. What is SI unit? It is in the form of like second, meters, that is and all as a SI units. So in order to calculate the power density, we have to know about the photon flux. Then what is the unit of photon flux? That is unitless currently, because it may be considered as a number of photons with the particular area and second, that is the combination of the all the unit. Then if we convert these things into the power density, we will get the SI unit as a watt per meter square for power density. Then as we know that we derived the two equation previously, let's consider the first equation, hc by lambda. H is a Planck's constant, c is the velocity of light, and lambda is the any wavelength, and with the photon flux, then you will get the power density. It is in the SI unit. SI unit maybe it containing the meter per second, and wavelength in any meters, and Planck's constant in joules. Okay. Now I want to in wavelength format. What is the wavelength? I want only in meter format. For that thing I will have another equation, that is multiplied with the charge of electron. So by multiplying the charge of electron I will cancel the joule unit, so I will remaining only the wavelength. Then if I want to only the energy is in electron format, then I want to get the electron volt. Then I have to multiply this charge of the electron and I have to consider the energy of the electron. Then I will get the power density in the form of watt per meter square, which is equal to in the form of electron volt. Then we will go for the spectral irradiance. So what is the spectral irradiance? It is a function of a photon with a wavelength and it is denoted as a F. And this spectral irradiance is the one of the characteristics of the light. The unit of the spectral radiance are watt per meter square. If we consider any wavelength, then it having per micrometer. So the final equation will be the watt per meter square with the wavelength micrometer. So finally, let's consider Earth, and this is a solar energy. It is coming from the a different angle. It can be like this due to some cloud. It will hit here and it will reflect like this. So at this thing, we will get the different energy bands for different wavelength. So if we plot wavelength from 100 to around 1000, we will get the different irradiation. Like I previously told that irradiation in this format like this. So as wavelength changes, irradiation also changes. That may be some, if it containing a very clear sun, then it will give the clear irradiation. So we can derive the energy and wavelength relation by spectral irradiance. So in this figure you can see that solar is radiating some energy. Sun with some different angle, it will be incident. As I told, it will hit some cloud or any gases, it will scattering out. Then it will hit to ground. So how we can plot for different wavelength, for different irradiance, I will get the different type of energy. So we will get this type of waveform using our spectral irradiance data. So how we can draw this one? This can be drawn using Python programming. So if we get solar irradiation data for a whole day, like if we get solar radiation from starting of the power plant to till entire year, if we have that kind of data, we can plot like this of data. So now we will see the all the spectral radiance and photon flux in this lecture. In next lecture, what we will go? We will know deep into the atmosphere effect and how solar radiation is coming into the Earth atmosphere and how it will incident on the solar panel. What is the air mass and other effect to the solar PV? We will discuss it in the next lecture. Thank you.